section 4.2.1, bound charges. So in the last video, we discussed how you can have some neutral atom. You can put that neutral atom in an electric field, and you can generate something that looks like a dipole. Okay. So you can create a dipole moment by putting something that doesn't have a dipole moment in an electric field. Right? Not everything, but many things. Okay. So now the question becomes, I put some macroscopic object in an electric field. Make that consistent. I create a bunch of dipoles because materials are made up of many atoms or many molecules. Okay, I'm not going to draw all of them. This series of dipoles, right, can be defined, can be described as an object that has a non-zero polarization. I put this bar on the bottom to say that that is a capital P, differing from this lowercase p, which is just a dipole moment. Okay. And the polarization is related to the dipole moment. It is a dipole moment density. So it's the number of dipole moments per volume. And the purpose of today, or this video, is to say, all right, let's say that we have this polarized object that has a bunch of different dipoles in it, right? Let's forget the fact that there was an electric field that exists to polarize my object. Let's just take an object that has a polarization, so some number of dipoles per unit volume, and figure out what is the field created by the polarized object. Polarized object. All right, that's what we're going to do right now. So let's remember what the potential is for a single dipole. One over 4 pi epsilon naught, the dipole moment, dotted with r hat over r squared. And if I want to know what the dipole, or what the potential is from a series of dipoles, I need to integrate over all of the dipoles, right? And since we have a dipole density, this polarization, we can use that. Okay, so I'm going to integrate over the whole volume of things that have dipoles in them. All right, 1 over 4 pi epsilon naught. My polarization, which exists at my prime coordinates, because that's the things that are polarized, dotted with r hat over r squared. Integrate that over all the charges, or in this case, all the dipoles. All right. And we could technically stop there, but that's not very useful. Griffiths shows us a nice little trick, which says that we're going to replace this with a gradient term. Okay, so I can go ahead and write this as 1 over 4 pi epsilon naught, still integrating over the volume. Now it's the polarization dotted with a gradient. I'm putting the prime because it's with respect to the prime coordinates, 1 over script r, d tau prime. And the reason for introducing this is that now you have an integral, and the integral has a derivative inside of that. And again, that smells like integration by parts. So I'm going to try to finish everything on one page here. So I'm going to move it over. That integration by parts gives you two integrals. It gives you 1 over the volume of the gradient of my polarization over script R d tau prime. And there's a minus sign, another integral over volume, 1 over script R, the divergence of my polarization integrated over all space there. Okay, we're going to invoke the divergence theorem for the first integral. Because I have a del dot p here integrated over the volume. So del dot p integrated over a volume is like a surface integral of p dot dA. So 1 over 4 pi epsilon naught integral over a surface now, 1 over script R p dot dA. Minus still that volume integral, 1 over script R del dot p d tau prime. All right. So I have two integrals I have to do here. The first is the integral of the polarization dotted with my surface, and the second is over a volume of the polarization dotted with with the gradient, with the operator del. Now you can leave it here, but we're going to keep going. The goal here is to say, all right, well, if I have a polarization dotted with a dA, I can kind of redefine that as, all right, some number of charges that sit on a surface, right? This whole thing, if I write it as, if I define a surface charge density sigma b as this, the polarization dotted with the surface vector, the unit vector normal to my surface, and I can also define a volume charge density as minus the dot product, the divergence of P. I can rewrite this whole expression here as two separate integrals that have different kinds of charge distributions associated with it. I have 1 over 4 pi epsilon naught, a surface integral of my bound, or I haven't said that word yet, but this is what we're calling the bound charge density. My surface charge density over script R dA prime plus 1 over 4 pi epsilon naught, a volume charge density over script R d tau prime. All right, and this is really, these both look like different potentials, right? This is the potential from a surface charge density and this is the potential from a volume charge density as defined here and here. So if you know the polarization, you can find out what these different charge distributions are, and then you can calculate the potentials. And I said the word bound. What does it mean to be bound? The subscript B stands for bound. So I have a bound volume charge density, and I have a bound surface charge density. Right, these are charges that are not free to move by definition, and it comes from the fact that the polarization is sticking charges in different regions of space, or it's either sticking at the surface or they're sticking. They're unable to move inside of the volume. Okay, we'll talk more about that later. So if you know the polarization of an object, which is the number of dipoles, the dipole moment per unit volume, you can calculate the potential of this whole system by defining the bound charge densities.